next type which we are having is the defects in the non-stoichiometric compound. Now what is non-stoichiometric compound? Then simply I will say the non-stoichiometric compounds are those compounds in which the ratio of the cation and anion is differ from the actual ratio of the cation and anion in a chemical formula. For example, suppose I have the vanadium oxide. The vanadium oxide VO, the molecular formula is VO. That means here the expected ratio of the vanadium and oxygen is 1:1 by the chemical formula. But when it is observed practically, then practically we come to know that here the vanadium is the ratio of the vanadium and oxygen is not 1:1, but the vanadium is in between 0.6 to 0.13. It is in the range of 0.6 to 0.13. That means the range was not 0.6 to 0.9. That means the range was not proper. So now this vanadium oxide, instead of having a molecular formula VO, it will have V0.6 oxygen or V0.9 oxygen. Similarly, if I am writing for the ferrous oxide, that is FeO. Now in case of FeO, the molecular formula is for ferrous oxide, the molecular formula is FeO, that is a 1:1. This is the ideal molecular formula. But when we talk about the experimental data, then practically it has been observed that here the inner ratio, the Fe is present in between the 0.93 to 0.96. That means this molecular formula changes to either Fe 0.930 to Fe 0.960. Means either you means the molecular formula will be somewhere in the range of these two. So these are called as a non-stoichiometric compound, where the cation and anion ratios are not according to the molecular formula, but it is different. Then here we are, means now in the case of here we are talking about the defects in non-stoichiometric compound. Means here due to the defects, the stoichiometric compounds are getting converted into the non-stoichiometric compound, and that's why we are getting such type of some relations. Now here we have two types of non-stoichiometric defect. The one is called as a metal excess defect and the second is called as a metal deficiency defect. Now this metal excess and metal deficiency defects are the two different types of these defects in non-stoichiometric compounds. So let's start with the first type. That is metal excess defects. Now in case of metal excess defects, again we have two types. The type number one, now metal excess defect means, simply I will say how to remember this. Metal excess means we know that the metals are made up of cations, that is a positive ion. So metal excess defect means where the cations are more in number compared to anions. Cations are more in number compared to anion is called as metal excess defect. Now here the cations are more in number. How the cations will be more in number? So there will be a two possibility. The number one, excess of cation, and the number two, deficiency of anion. So there are the two possibilities, the excess of cation and the deficiency. Excess of cation means the cations are more in number, or the second one is the deficiency of anions, that is anions are less in number. Let's start with the second one, that is the deficiency of anion. Let's see what it is. Deficiency of anions. Now let I'm considering sodium chloride solid, that is again a ionic solid which contains cation and anions. So this is an ionic solid which is containing, that is, I said, it is an example of sodium chloride, Na plus and Cl minus. These are Na plus Cl, Na plus and Cl minus, and they are in the ratio of 1:1. Now what happens due to the means what happens in the case of, like, if I'm saying deficiency of anion, that means what happens in the case of this, that is in this defects, the anions are missing from their places. Anions are missing from their places means, for example, there is an anion. Now this anion will now this anion migrate from here so that a vacancy is created. So anions are missing from the places. Now there is a no anions, I can say, right? When the anions are missing, that space is occupied by the electron. So electrons comes here and it occupies the space which is left by the anions. So electron is trapped here, I can say. In this case, now I can say that if you are counting the number of cations and number of anions, you will come to know that there are total 12. Initially there was 12 cation and 12 anion, but since the anions migrate from its actual point, so now we have 12 cations and 11 anions. Means I can say that ratio has been disturbed, because in case of NaCl, the Na plus and Cl minus ratio is 1:1, which has got disturbed now because of the migration of the Cl minus ion. So now the ratio is not proper, or according to the molecular formula, that's why it is considered as a non-stoichiometric defect. Electrons come since the at the place of cation, at the place of chlorine and the electrons comes, that's why I can say the neutrality remains maintained, that because the Cl also carry -1 charge and that position is now gained by the electron which also carry the -1 charge. So now I can say that this cation and anions are not equal in number, even if their charges are balanced, means there is an equal number of the positive and negative charge. So ultimately, after the missing of the electron also, the anion also, I can say the solid is a neutral in nature. Now what happens, how this electrons, question arises that how this electron comes and why the chlorine is migrating from its place. There are the various questions. Now let's see what happens. Suppose I have this NaCl solid. This NaCl solid which contains large number of cations and anions. That is sodium ion and chlorine ion. Now I am passing sodium vapor from this, or it is placed in a sodium vapor. Sodium vapor, so what happens, the sodium vapor get attracted on the surface. These are the sodium vapors. So sodium vapors get attracted on the surface. So what happens, this negative ions, that is, or this chlorine or negative ion chlorine, it diffuse to the surface, means chlorine ion migrate to the surface and it comes here. So this is now chlorine ions. And once the chlorine ion diffuse to the surface, that means in a lattice or in a solid, the chlorine, now there will be no chlorine. The chlorine has migrated here, that means now there is no chlorine. And once there is no chlorine, means I can say that this is an anion vacancy has been created. Now when the chlorine comes here, the Na lose and sodium, this was the sodium atom. So once the chlorine comes here, the sodium loses electron and becomes Na plus an electron. And the electron which is lost by the sodium atom of the sodium vapor, once the chlorine comes to this, then this electron comes and occupy this area. And hence we say that in this case, the anions are missing, and that anion, the space is occupied by the electron. So from that, where that electron comes, the electron comes from the sodium, which is lost, which is lost by the sodium atom. So this is about the deficiency of anions. Now when the electron is trapped in a lattice point, then it is called as F center, and this F center is responsible for the coloring of a compound. Sodium chloride, due to this, see when this thing happens, means in a sodium chloride, when the anions start migrating and the electron occupy their position, then as the defect goes on increasing, the color of the sodium chloride start changing and it get converted into the yellowish color. Sodium chloride, which is white in color, get converted into the yellowish in color because of this formation of electron. So since there is an electron, so there is an excitation of electron, means the color of the compound keeps on changing. And the second thing, that electrical conductivity has also been increased. Since there is electrons, so electrical conductivity is increased. So this is about the first one, that is the deficiency of anions. Now let's say the second one, that is excess of cations. So it's a very important one, that is the F center. F center is, whenever question comes on the F center, just it's a deficiency of anion, and generally the question is asked in MCQs for the color, that is a defects responsible for the coloring of compound, then answer is F center defect. Then the next is excess of cation. Now let's see what happens in the case of excess of cation. As the name says, the catans are more in number, and ultimately we are doing the same thing, that is a metal excess defect. So here in this case, now in the case of this excess of cation, what happens? Now in the case of excess of catans, uh, the catans are more in number. For example, suppose this is the zinc oxide. The zinc oxide, when the zinc oxide, where the zinc and oxygen, zinc is a cation and the oxygen is an anion, they are in the ratio of 1:1. Now what happened during the heating? When the zinc oxide is heated at a high temperature, then during that process, the zinc oxide, the zinc ion and oxygen is formed. When the zinc oxide is heated at a very high temperature, then zinc ion is formed, and O minus, it was a zinc 2 plus and O minus undergoes oxidation process, O minus undergoes oxidation process and get converted into O. So the electron which is lost by O minus is here, right? So it's not half, okay. So electron which is lost, it is here. So we are getting a O2 minus. Each oxygen loses 2 minus charge. So each oxygen loses 2 electron. So ultimately, the oxygen become a oxygen minus get converted into the oxygen gas. It leaves the container, or it leaves the crystal lattice and get mixed with the surrounding. And due to which, since the oxygen minus is getting converted into the O atom and is getting converted into oxygen gas, that's why I can say the number of oxygen ions goes on decreasing. And since the number of oxygen ion goes on decreasing, so the number of zinc ion goes on increasing, that is the catans increases, because O minus and zinc plus, both zinc 2 plus and O2 minus both are present in the ratio of 1:1. But since the some oxygen minus oxide ions are getting converted into the oxygen gas, that's why I can say the oxide ions are getting reduced, and the number of zinc cation goes on increasing. That zinc cation which is increased, it occupies the some lattice interstitial spaces like here, here. So some zinc ion is, so the zinc ion occupies some interstitial spaces, and the electron which is lost here, that electron also occupy the interstitial space depending on the number, how many electrons has been produced. So if one zinc 2 plus ion is increased, then there is a 2 electrons will be produced. So ultimately here again I can say the number of oxygen, the catans are more in number, you can count, but the anions are less in number, but ultimately the charges are going to be same. Suppose there is a 1 plus plus, so electrons has been increased. So this is about the excess of cation, and this excess of cation is because of such reactions, like where the oxide ions get converted into the gaseous state, it leaves the crystal lattice, and so zinc ion increases. So here again, this is a non-stoichiometric defect. As I said, that the ratio of the cation and anion is not according to the expected chemical molecular formula of a given solid. Then after metal excess defect, the next we are having the metal deficiency defect. That is the second type of the defects in non-stoichiometric solid. So second one is, this was the first one. So in metal in a metal deficiency defect, we are again having two types. Like here we have, it's a metal deficiency defect, that is the catans are less in number and the anions are more in number. So there will be a two type. Catans are less in number, that is due to the deficiency of cation. So catans are less, deficiency of cation, so that number of catans will decrease. And the second type is the excess of anions. So now let's talk about the first type, that is deficiency of cation. Now in case of deficiency of cations, the cations are less in number. So again, like this is an ionic solid. Cation, anion. Now in the case of this deficiency of cations, in the case of this defects in solid, what happens? For example, suppose I have, this is a ferrous oxide. Ferrous oxide means which is FeO. Now here the ferrous is, Fe is present in the form of Fe2 plus An. Now let I have 3 Fe2 plus An. So 3 Fe2 plus An, that is total charge is 6. Now this 3 Fe2 plus An is getting converted into, these three combinedly getting converted into 2 Fe3 plus An. What? They are getting converted into 2 Fe3 plus An. So ultimately, now what happens after the formation of 2 Fe3 plus An in a solid, the 3 Fe2 plus Ans will be missing. They will leave the surface, and instead of 3 Fe2 plus An, how many Fe3 plus An will get introduced? 2 Fe3 plus An. So 3 places are vacant, and out of which only 2 places will be occupied. That means again 1 Fe2 plus An will be considered as a missing. That is, 1 place of a cations will be missing. For example, this was Fe2 plus, this was Fe2 plus, this was Fe2 plus. They combine together and they form Fe3 plus. Missing, missing, and missing. Out of these 3, Fe3 plus, Fe3 plus. But this place will remain vacant. So here this places remain vacant. So now ultimately what happens? The charges remain same. That is, now Fe3 plus and Fe3 plus. Charges remain same, but the number of cations has been decreased. So what happens in case of deficiency of cation? In case of deficiency of cation, the cations are missing from their places, and just to maintain the neutrality of the solid, some surrounding cations will have extra charge. Like here it was only plus 2, now it will have plus 3 charge. It was plus 2, this will have plus 3 charge, something like that. That is, surrounding cations, surrounding ions or cations will have the extra charge, so that the solid should remain perfectly neutral. And now in this case, since the cations, now here as I said, some Fe2 plus An is missing. So here the number of Fe2 plus An is getting decreased, and that's why here the ratio get disturbed, and instead of having FeO, that is 1:1 ratio, we have such type of ratio 0.93. It means 0.7 things Fe is missing from their places, and because they has got converted into Fe3 plus ions. Then second one, that is deficiency, or after deficiency of cation, the next is excess of anions. Excess of anions. Now what happens in case of excess of anions? Now let's see. Excess of anions. Now in this case, the anions are more in number compared to the cations. Anions are more in number. So what happens in this case, there are the certain anions, means there is some extra anions comes and they occupy these interstitial spaces. And extra anions are getting occupying, since they are occupying the interstitial spaces, that's why the number of anions increases and number of cation decreases. And since the anions comes, extra anions comes into the picture, that's why the negative charge increases. So to maintain the neutrality of the solid, there is a certain particular, there will be some cations which will have the extra charge. Like this cation is having plus 2 charge. Initially it was plus 1, but once the 1 anions come, this will have plus 2. Suppose there is a 1 anion more. So this some cation will have one more extra charge. So ultimately, cation by carrying the extra charge maintain the neutrality, but due to the presence of this extra anion, the ratio of cation and anions get disturbed, and that's why we say that here we have the more number of anions and less number of cations. That means it is again a non-stoichiometric defects. So in a non-stoichiometric defects, ultimately we are having two different types of defect. That is a metal excess defect and metal deficiency defect. Metal excess defects, that is a cations are more number. There is a two possibility for having a more number of cations. That is, number one is a deficiency of anion, which is known by the F center defect, and the second is the excess of cation. This deficiency of anions and excess of cations, since the electrons comes into the picture, that's why the conductivity increases, as well as during the defect the color keeps on changing. Zinc oxide is again, since the electron comes into the picture, zinc oxide initially white in color, but as the defects goes on increasing, this also get converted into yellow in color. Similarly, as the defect increases here, the NaCl also becomes yellowish in color. That means as the defect increases, this in the case of this, the color change takes place. Then second is a metal deficiency defect. Deficiency, again the two types, deficiency of cations and excess of anions. Deficiency, that is the cations are less in number and the cations are less in number because of deficiency, and here the cations are less in number because of the extra anions which are occupying the interstitial spaces. Overall, due to these defects, the compound in the compounds, the non-stretching, that is the ratio of the cation and anions get disturbed. Now the next type which we are having is impurity defect. Impurity defect which is observed only when some impurity is added in a given substance or in a given solid. So the next type we have impurity defect. Again, there are the two types of impurity defect. The first one is substitutional impurity defect. Substitutional impurity defect, and the second is interstitial impurity defect. Now let's see what are these two types, that is substitutional impurity defect and interstitial impurity defect. So the first one, substitutional impurity defect. Here now in case of substitutional impurity defect, for example, suppose I have this copper solid. The copper solid means each of them are copper atoms or copper cations. Okay, so this is the copper solid, these are copper atoms, and then after that I'm adding zinc into this. So when the zinc is added into this, means I'm trying to make an alloy of zinc and copper, the alloy which is a mixture of two or more metals. So I'm just mixing zinc with it. So when the zinc is mixed with the copper, and now in this case I can say the zinc is acting as an impurity for the copper, because once the zinc is added, the purity of the copper will be destroyed. So when the zinc is added into this, what happens? Now when the zinc will be added, there will be two possibilities during the mixing. Either the zinc will start substituting this copper atom, or it will occupy the void depending upon the size of a zinc atom and the copper atom. If the size of a zinc atom is approximately equal to the size of a copper atom, then in that case I will say that the zinc will start substituting copper atom. The zinc will substitute copper. So all the copper atoms, some of the copper atoms will be substituted by zinc if the size is same. And if the zinc is smaller in size, then instead of substitution, it will start occupying the small voids which are left between the zinc, left between the copper. Now I know that in periodic table the zinc and copper comes one after each. Means they are just one after each other. That is the copper having atomic number 29 and the zinc have the atomic number 20. So after copper zinc comes, that means the size is not in the, there is not a very big difference in the size of a copper and zinc. That means they have approximately same size. And due to the same size, what happens? Some of the copper atom gets substituted by zinc. So this was initially copper, now it is zinc. Again, this was initially copper, but now it has become zinc. Initially a copper, but now zinc. So this is substitutional impurity defect, in which an actual atom or the actual particle of a solid is replaced by the impurity. That's what is called as substitutional impurity defect. And this mixture is called as a brass. The brass, which is an example, which is an alloy of copper and zinc, which are present in the ratio of 3:1, and you can see the ratio again 3:1, 3:1. So this is the brass, which is a mixture of copper and zinc. Another example of this I can say, suppose I have two solids. Again, I have an ionic solid. I have ionic solid, that is Na plus Cl minus, Na plus Cl minus, that is, it's a sodium chloride. Again, this is Cl minus, Na plus. So here we have Na plus and means sodium chloride ionic solid. Now in the case of sodium chloride ionic solid, suppose I am mixing it with the strontium chloride. Strontium chloride, that is Sr2, SrCl2, which have strontium ion and chlorine ion. So since the anion is same, so there is no problem with respect to the anions. Now we are adding strontium ion. What will happen? What the strontium will do? Now the strontium ion which carry positive charge, it will start substituting Na plus ion. That means it start replacing sodium ion. Now the sodium ion, see, during the substitution the charges should be balanced. So during now here strontium I can say +2 charge and Na carry the +1 charge. So when one strontium will come, ultimately how many sodium will be replaced? Then answer is that 2 sodium will be replaced. So suppose if I am adding strontium ion, then here the 2 sodium ions will be replaced, means this sodium ion plus and this sodium ions. But out of this, one place will be occupied by the strontium ion. That means the strontium ion will occupy this space, but Na plus and Na plus will remain vacant. That means one strontium replaces 2 sodium ion, out of which one space is occupied by the strontium while the other space remain vacant. That means because of this, in this impurity defect, because of the addition of strontium, the vacancy has been also created, and this solid has been got converted into the non-stoichiometric compound, because here the number of cations and anions ratio has been changed as the some cations are less in number. So some of the example of substitutional impurity defect comes under this non-stoichiometric defects also. Now the next is an interstitial impurity defect. Interstitial impurity defect, now what happens in this case? Now in interstitial impurity defect, for example, suppose this is an iron metal, that is Fe, all are Fe atom, and I am adding carbon into this, carbon which is very small in size compared to the Fe. And so when carbon will be added, as I said, there will be two possibility, either the substitution, or if the size is approximately same for the carbon and Fe, then carbon will substitute, or if this is smaller in size, then will occupy a void. So as I said, the carbon is a very small in size, and being a small in size, it starts occupying voids. May occupy all the voids or may occupy only some void, depending upon that how much carbon is added. So here the impurity which is added, carbon is acting as an impurity. When the impurity is added, the impurity being a smaller in size, it is occupying the interstitial, that is a spaces, that is a void, and that's why the name is given interstitial void. Now this happens when the iron, see, pure iron is considered as a soft iron. So for increasing the hardness of the iron, the carbon is added into this, and carbon occupies the interstitial spaces, so that structure becomes more compact and the hardness increases. So interstitial impurity defect is a one in which the impurity which is added, being a smaller in size, it start occupying the voids, that is the interstitial spaces. So this is about the impurity defect, and which occurs only when the impurity is added. Suppose if the zinc was not added, no impurity defect. If the carbon is not added, suppose if I am not adding a carbon, again it is going to be a pure, that is again it's a not a, means the impurity defect will not comes into the picture. So this is about impurity defect.